I will begin with a word of prayer. So, Heavenly Father, we thank you again for your many blessings to us, and just ask you to guide our thoughts today, help us to glorify you in what we do, and understand a little bit more about conformal mapping, Lord. In your name I pray, Lord Jesus. Amen. So, I have a few different things I want to talk about today. So we've looked at, some particular sneaky ways to solve Laplace's equation, basically by judicious choice of real or imaginary parts of well-known functions like the logarithm, or just az plus b even, right? That serves to play an important role. But now I need to talk about a slightly more exotic idea, which is the technique of conformal mapping. And so I'll try not to spend too long on this, because I also want to talk about an important class of conformal maps known as Mobius transformations, or also known as fractional linear transformations. So let's get straight to it. Suppose we've got in here, x and y, so here we've got the z-plane, right? And then we've got some transformation f, all right? And then over here, you've got u and v, you've got the w-plane, right? And let us suppose that we have, on the one hand, over here we've got some kind of region, which I'll draw like a lima bean, and we could call that S for lack of imagination, and then F maps that over to here to, and that is of course not a very good representation. Whatever it does, I don't know. Maybe it just kind of makes it into more like maybe it just stretches it out or something. I don't know. It does have to do it conformally, though, right? So there's actually some pretty strict conditions on what can happen locally, at least, because the angle between curves has to be preserved in as much as the derivative of f is non-zero as a complex holomorphic map, right? And when you study it more carefully too, what you learn is that if there's sort of an orientation, if this S is simply connected, perhaps, you can talk about the boundary being positively oriented in the counterclockwise sense, right? So like that way. And it turns out that, it takes the inside in here over to the inside over here. So like it's not just that it maps the edge, it also maps the interior as well. And so let's see here. Like that. All right. So, if we think about it, we've got a solution then. If let me put it in different words. If I have, right? If I have phi xx plus phi yy equals to 0 on the boundary of S, all right? So the boundary of S is the edge of S. So that would be a solution to Laplace's equation. If it's a solution to Laplace's equation on the boundary, and phi restricted to the boundary is given, So you have particular values on the boundary, right? Boundary values. Then one of the things is that over here, the boundary of the image is the image of the boundary. So like the edge of this maps to the edge of that. It's one thing. And let's see here. I could define, so that's one thing. And it may also be helpful to look at, suppose I have, let's say, psi with values specified on, the boundary of f of s, which I probably should just call this thing t. Let me call this thing t over here. So on the boundary of t, all right? And you've got psi uu plus psi vv equals to 0. So we've got, a solution to Laplace's equation over there that has specified values on the boundary of t. It becomes interesting to ask the question, can we take a Laplace solution here and move it back over here and vice versa, right? Can we move solutions from one context to another? Yeah.
What and psi, where did they come from?
They are a solution to Laplace's equation, and they come from our dark imaginations. So, or perhaps more accurately, techniques we talked about last class. So, washers, wedges, walls, those kinds of things. Okay, so can you tell me how we can get from here back to here using f, right? So more specifically, we could think about phi as a mapping, right? It's a mapping from S to the complex plane, right? It's a complex valued map, at least in principle. You could look at real valued phi, and you could look at real valued psi too, but I'd just like to keep it complex because it's a little bit easier to think about that as it interacts with our theorems. So if I have from here, if I have this goes from S to C, let's see here. What if I was to look at, can I compose F? F takes in things from Z, right? So I think, phi of Z I think about in here, so to speak. So what I'm trying to say is I could look at, for example, I have gotten derailed. So how about this? I could write this. I could say phi of Z. I could try building it like this. It is f, no, my bad, psi of f of Z. That's one thing I could do. See, because the natural input into psi is like a W, but a point over here is something like, we're looking at W equals f of Z. Okay, so it makes sense to put in an f of Z into the psi because psi takes W in its domain. And how could I turn this around? How could I build a psi of W, for instance, using phi, if it was given? So let me put some interpretation here. So we're constructing phi given psi. All right, that's the idea here. That's its implementation. On the flip side, if I knew the inverse map, right, f inverse, then I could also say, well, psi of W I could build from phi of what? F inverse of W. So here I'm building psi given phi. All right. Now, the typical application here, what we do is we write down a known solution in the W plane, and we'll be sneaky in our choice of the map to take that solution over here and pull it back to the Z plane. That's typically what's done. All right. So let's look at an example of that. So Do 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 do. So we're in section 7.1 if you guys were wondering. Let's see here if I can find a relatively simple example. Well, tell you, forget about more complicated. Let's try to work a really simple one, relatively simple one. Example 1. All right, and so x, y. So I'll let you guys over here u v. And let's just write down a solution to Laplace's equation in the w plane using the techniques we talked about last time. Like let's write down a solution, say on the on this half plane, for instance, such that I'll make it relatively simple. So I want to find a solution here. So I'm thinking of my t as being, you know, u plus iv such that u is greater than 0. Okay. So that's the region I'm solving Laplace's equation on. And let us suppose that we want to put psi equal to 42 up here. All right. Psi equal to 42 there, and we'll put psi equal to, what do you guys want for the below down here?
0.
Psi equal to 0. Okay, I like it. So psi will be undefined at the origin because it's got to have a jump there. So how do we do that? How do we achieve that? We'll do that.
A linear combination of args?
A linear combination of args, I like it. So we could use, for instance, psi of w equal to, like a arg w plus b, for instance. I think that'll work because it's undefined at 0. Okay. And admittedly, I'm okay. So let me flip back over here for just a second, and then I'll come back. So I did need to do a little bit of theoretical weightlifting, so to speak, over here. So my point over here, guys, with all of this diagrammatics is simply this: if f is holomorphic, right, and psi is holomorphic, you have the composition of holomorphic maps, which is once more holomorphic, which means since the component functions of holomorphic maps are solutions to Laplace's equation, it follows then that this is harmonic. Like the fact psi being harmonic and f being complex differentiable means that psi will also be harmonic. So again, just using the fact that the composition of holomorphic maps is holomorphic, we automatically get that the solutions built in this way are going to be, in fact, harmonic. And so we don't actually need to use a complex solution, right? Because we can focus on just the real part or just the imaginary part of this transference, and we can trust that we're going to start with a Laplace solution, and we're going to end up with a Laplace solution if we track back through the appropriate map. All right, so, and this is all derived a little bit more systematically. If you read section 7.1, it's there. But I think you'll probably be less confused as I actually show you an example. So let's continue with that. So my point of all that was this was not a complex valued function. This is a real valued function. So it's a real harmonic solution if I choose. And so pick a point. How about I minus I, right? So psi of I is equal to a times pi over 2, right, plus b. And psi of minus I is what? a minus pi over 2 plus b, right? Now this is equal to 42, and this is equal to 0. Why? Because you guys said so, right? So subtract these equations. What do you got? We've got ourselves pi times a equals to 42. Therefore, a is apparently 42 over pi. And that makes b equal to what? A times pi over 2, right? Which would be 42 over pi times pi over 2, also known as 21. So lo and behold, after a little bit of algebra, we have located our desired solution to Laplace's equation simply as psi of w is equal to 42 over pi arg w plus 21, right? That solves Laplace's equation on the half plane where the real part of w is positive. Do you guys agree? Okay. Now, we can take, any map you like, going from here to here, and then to make it most interesting, perhaps we should I don't know. I guess we could try the reciprocal map, see what that does. That's probably going to do something kind of funky. Like, what is f of z equal to 1 over z? What's that do? My question is, what is the inverse image? What's the inverse image of t? Which points in the z-plane mapped to that positive half plane if we use the reciprocal map? No ideas? What is f inverse? Oh no. 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 So you want f inverse of f of z to be equal to z, right? Or if you like, yeah, so in other words, we're trying to solve f inverse. All right, you can look at it this way. I usually look at it this way. W equals to f of z, right? To find the formula for the inverse, solve that for z. Solving for z gives me z is 1 over w. This will be the inverse function. To give a more dramatic example, if I had f of z equals to, I don't know, z squared plus 7, and I wanted to find the inverse function. Well, first of all, that's not really a a well-defined. I mean, you got to attach strings to that, okay? But I would be trying to solve this for z, and I would find that z is equal to plus or minus the square root of w minus 7. Now, that's a principal square root, because at best you can give a local inverse for this function, because this function is not 1-to-1 everywhere, right? So I could choose the plus square root. That would be an inverse function to z squared plus 7, restricted to a certain domain. All right. Likewise, the minus would be a inverse function to z squared plus 7, restricted to a certain domain. Okay, so that's just a crash course on how you calculate the inverse function. You set w equal to f of z and solve for z. That gives you the inverse functions. All right, so back to my question. What's the inverse image of that half plane? How do you figure it out? So we're trying to figure out what's f inverse of t, which would be, I mean, we can literally look at f inverse of w such that w is in t, right? Because the inverse map exists here. which would be 1 over w, right? Such that w is equal to, like, what? We could say, r, I guess we could say s e to the I beta, perhaps. Minus pi over 2, less than beta, less than pi over 2. If you want to, present it in terms of polar coordinates, great. And the s is what? Positive constant. So what's that? That's really, e to the 1 over s e to the I beta, such that s is positive and beta is ranging I think it's kind of annoying. Rats. Well, what happens here? So this is really 1 over s e to the minus I beta, right? So it's a little bit funny, because if I multiply the inequality by minus to get my question is what happens with minus beta, right? That describes the angles for the image. See? So like the point in the inverse image, it has e to the minus I beta. So to understand where that goes, I have to understand what inequality bounds minus beta, right? So to get that, I multiply this by minus 1. What happens then? I get pi over 2. When I multiply by minus 1, I have to reverse the inequality, right? Which means that we're still mapping to the half plane. Dang it. Well, this is dumb. I'm trying to give you a map which like moves my set T somewhere else in the z-plane, and I have managed to pick a map which fixes T. Like what this proves is that f inverse of T is the same stupid set. Although it does do some weird stuff. So like I've studied the reciprocal map before. The reciprocal map turns the unit disk inside out. So it's not this. It's a little bit more. It's a little bit trickier than that, because like what happens under this map is if you were to look at like the unit, if you were to look at this set right here, this particular subset, all right, and you were to look where that goes to over here, it would go to all of this. On the flip side, everything outside goes inside, I think. So like the red part maps over to here like that. So, yeah. So in terms of like what happens to the set, it's not particularly interesting here, so I'm sorry about that. You win some, you lose some. But we can still write down the formula. The formula is still interesting and perhaps surprising. I should have just done like a square root map or something. That would have been weirder. If I'd taken the square root of that, I would have got like a quarter plane. That would have been smarter. I should have done that. Oh well. I was trying to make it easier, and in the process of making it easier, I made it weird. All right, so here's our solution. Now I want to write down the corresponding solution in the z-plane. So I follow the template. Phi of z is what? It is psi of f of z, right? Which is psi of 1 over z, given my current construction. Yeah? Now, I can be more specific here. This is actually, in terms of real calculus, real trigonometry, this is 42 over pi inverse tangent of v over u. That's plus 21. That's actually what we got here, because it's where u is positive, so we can use the inverse tangent to get the argument there. So the question then becomes, what is the u and the v here? Well, this is psi of, x minus iy over x squared plus y squared. That's the formula for the reciprocal function, which tells me that I'm going to put u as x over x squared plus y squared, and I'm going to put my v as minus y over x squared plus y squared. So then this is, in fact, 42 over pi inverse tangent of v. Well, so this is the annoying thing, is like all the coolness, it evaporates in the fraction here. Like v divided by u, the x squared plus y squared be canceling, and you just get what? You just get
minus y over x.
Yeah, minus y over x, exactly. So we actually get 42 over pi minus y over x, of course, plus 21. And that is what the technique of conformal mapping would suggest we do if we were to use this reciprocal map with that given Laplace equation over there. And then you can study it and see how it works. It's not defined. So like x equals to 0, technically speaking, isn't even really defined, is it? We have to consider it in like a limiting sense, So let's see here. Y equals to 0. I should get. I guess I get 21 for y equal to 0. I don't know what that means. Well, that's out here. I guess that makes sense. The 1 maps to 1 under f. 1 over 1 is 1, and like psi of 1 is 21, and phi of 1 is also 21. I'm trying to see something more interesting. Let's see here.
Does it map to the average?
No, it's nothing like that. I don't believe so. Sorry, guys. I am trying to think of something to say here. So where does the inside, like this, should map to like up here. It turns this thing over, I believe. There's something perverse about this example. I can't put my finger on it. Not in a bad way. Not in a bad way. Sorry, I'm stuck here. It's fine. I mean, it illustrates the idea, but it's not a great example. Let's go on and let's put this thing out of its misery. So, to build better examples and more interesting examples, we really need the Mobius transformation. So let's talk about those. All right. So here's a definition. What is it?
I've never seen Violet laugh that hard. Wait. Violet, I want to see. Her whole body's just shaking.
I don't understand.
She keeps laughing at me.
What?
She keeps laughing at me.
Oh, okay. All right. So if we look at f of z equal to az plus b over cz plus d, this is a so-called fractional linear transformation, or you could say FLT, or a Mobius transformation. Provided we have a particular condition on A, B, C, and D. All right. So I'll make sure I haven't messed up my letters. Bless you, bless you. So here, come on. So AZ plus B, CZ, okay, cool. So we need that AD is not equal to BC. That's necessary. And I think, I want to say that there's, I don't think they can all be 0, can they? Oh, true. Fair enough. So I guess that's it. So the thing is, any Mobius transformation can be looked at as a composition of translations and inversions and dilations. So like a translation is what? So you have like T of Z is equal to, say, Z plus Z naught, right? That's a translation. All that does is it shifts the complex plane over by Z naught. What is it? You just got a case of the giggles? All right. I need to start giving quizzes in here, obviously. Let's see here, dilation. So this is something of the form, say, I'll say T1. T2 of Z is equal to like AZ. That's a dilation, all right? So you're just multiplying by a complex scalar that has the effect of stretching out and rotating, right? I guess to be fussy, you could split that further into I guess this is technically a complex dilation. Some people might say A has to be real to be a rescaling, and then if you had, if the you can write A as, like its radius times, its magnitude times e to the I theta. It's going to rotate points by theta, right? And then, of course, you have inversion. So that's the thing that just took us for a ride in the last example, all right? And you can actually show that you can write an arbitrary fractional linear transformation as a composition of these three things, right? So can you guys see how? Yeah? No? Okay. All right. So first of all, if you have these two things, you can put them together. You can build things like AZ plus B, right? Anytime you have a linear map, that is a composition of a dilation and a translation, right? See, because you could rewrite this as like A times Z plus B over A, right? And then this would be, I should probably use like a different notation, like, well, anyway, let me stop. So this is clearly a composition of the dilation by A and the translation by B over A, right? Okay, so that's one thing. And so, let's see here. well, I guess it's not especially interesting, like the precise argument, but it is just a bit of algebra that you can rewrite this explicitly as a composition of these three things. All right. So what does that mean? So I guess my question to you would be, what happens with these mappings as you think about, for instance, a circle? What happens with a circle with a translation? What's it do to a circle? Moves its origin, right? So it's still a circle, right? Translation of circle is still a circle. How about dilation? What's the dilation do to a circle? No, it actually still keeps it a circle.
It just changes. Yeah, it just scales.
So because what it does is what this has the effect of doing is, let's say, like magnitude of A times e to the I beta times z. So what that's doing to every point on the circle, you could think of it as rotating the whole circle by beta, and then it's inflating all of the points by the same scale factor A. But I agree, it's not entirely clear that takes circles to circles, but it does. And inversion also takes circles to circles, but I'm lying to you now. Actually, I'm lying to you about the dilation being entirely clear too, because if you think about a particular circle, right, like this one, right, what if the circle goes through the origin? You know, I mean, is it still clear that if I multiplied that by, you know, I don't know, 3i or something, is it still going to, I guess it's still a circle through the origin, isn't it? Because like if I multiply by I, it's going to rotate by 90 degrees and then expand it by 3. I don't know if it's entirely clear. But I also know that I don't have enough time today to prove that to you. It took me a solid hour of class, well-prepared, well-rehearsed class, to prove that in fact the Mobius transformations take circles to circles in general. It is actually quite technical, the full proof. Yeah.
Do you have a video on that?
Yeah, I do. I think I do. I sure hope I do, because Daniel, he erased that hard drive. But I think it's still there.
Did you really?
Yeah, I put Windows on that drive, and then it erased my 2 terabytes of videos. It's like 2019 to 2022, something like that. I know. He's a good son, though. He's a good son. And I mean, he was trying to do something good with it. Anyway, whatever. So, so here's the thing. A Mobius transformation, it's not at all clear. Like one of the things that's not, okay, so like, to me it's not, I mean, I want to believe that a dilation, translation's obvious, right? It maps circles to circles, right? But inversion, what does an inversion do to a circle that goes through the origin?
Is it bounded or?
I mean, let's work it out explicitly. So if I have, for instance, like what's a good circle that goes to the origin? How about this one? Let's make it as easy as it can be. How about this guy, right? This is what? X minus 1 squared plus y squared equals to 1. Let's say the circle of radius 1 that goes through 1. That's its equation, right? So I can parameterize that. And the parameterization is z is equal to 1 plus cos t plus I sine t, yeah? That's a parameterization of that circle in the complex sense. What happens when I reciprocate that? So like what's 1 over z in this context? Well, I can calculate that as z bar over zz bar, right? Let's do that. So you've got 1 plus cos t minus I sine t divided by 1 plus cos t squared plus sine squared. And let's work that out. How's that work out? So we've got 1 plus cosine of t minus I sine t divided by 1 plus 2 cos t plus cosine squared t plus sine squared t. Oh, look at that. Look at that. What just happened in the denominator? Yeah, we got 2 plus. So it looks like we can rewrite this as 1 plus cosine t minus I sine t divided by twice of, well, 1 plus cos t, right? Which we could rewrite as 1/2 minus I times the sine of t divided by 2 times 1 plus cos t. So that's the image of the circle under the reciprocal map. Can we understand what that is? What's going on here? So let me keep track of where things are, right? This would be t equals to 0 in my parameterization. Here's t equals to pi over 2. This guy's t equals to pi, and so forth, all right? So we've got this counterclockwise. And so what happens with pi?
Goes to 1/2.
It's worse than that.
Well, it's up to pi.
So I guess we have to approach it in the limiting sense, right? What's the limit as we go to pi? Like what that might be interesting. But that's what's the limit as you go to pi? You got what? 0 over 0, right? So L'Hopital's rule on that, I get a cosine over looks like a sine. So it's bad. It diverges in the limiting sense as well. Let's see here. So
And with the upper and lower limits also let's say they cancel.
I think pi is the only problem. I think everything else will like go to something. Like let's pick 3 other points. Where does t equal 0 go?
I mean like t from above, or pi from above, pi from
Oh yeah. I think both. Any which way you feed 0 into the reciprocal map, it's gonna blow up. So, all right. So what happens then? You guys tell me where t equals 0 go. 1/2. Is it just literally 1/2 in the 1/2? So do we want to think about? Let's think about this as w. All right. Well, fine. There's always an issue whether you want to think about transforming something from the z-plane back to the z-plane again, or whether you want to think about mapping it to a w-plane, which is different. This is 2 different viewpoints. So if I'm thinking about to the w-plane, so you said I got a 1/2 for t equal to 0. T equal 0 give me 1/2. All right, great. What does t equal pi over 2 give me? I mean, excuse me, you said this is t equals 0. Okay, t equals 0, give me the 1/2. T of pi over 2 gives me what?
Yeah, 1/2 minus I over 2.
1/2 minus I over 2?
Yeah.
All right, so this is a 1/2. Then we have a 1/2 minus I over 2. So if I did it right, it should be the same distance, because it's like just 1/2 down, right? Yeah? So it's that point minus I over 2. So it's the same distance from the origin down as it is over for the first point. How about minus pi over 2? Where does that take us? 1/2 plus I over 2. Okay, there we go. Why don't you guys try plugging in something, see if you can, if somebody can work out for me what happens at like 3 pi over 4. Ah, good grief.
Probably
Just a little bit above it.
okay.
I'm going to chalk it up to about right here. The larger point here is if you look at this formula, the real part's a half, and the imaginary part, it diverges to plus infinity one way, and it diverges to minus infinity the other way. So like if we studied it more carefully, approaching from above versus approaching from below, one would go to like minus infinity, the other one would go to like plus infinity. I'm not sure which is which without further study, but the larger point is under the reciprocal, this circle maps to a line. It maps to a line. And so what we can say is that Mobius transformations map circles. What they do is they map generalized circles to generalized circles. And so a generalized circle includes a line. And so to understand that, we actually need to understand a little bit about the Riemann sphere, all right? And so the Riemann sphere is covered in the textbook back, let's see here. Let me just draw a picture for you guys. Although, like, there's two different popular models for the Riemann sphere. The one that you maybe, if you've seen me do this in another class, I did not use this model. This is the model I don't intend to use. But it's fine. I mean, the formulas are for it in the book. So here's basically the idea. Here's the complex plane, and you can think about this. It's the Riemann sphere. So the Riemann sphere is, in his notation, x1 squared plus x2 squared plus x3 squared equals to 1. And so the down here, you can think of this as the complex plane. So we basically have, well, here's his notation. He says z equal to x1, x2, x3 on the Riemann sphere is the project is he says that if this is the projection on the Riemann sphere of the point Riemann sphere of point z equals to x plus iy. The way it works, the formulas for it are x1 is the twice the real part of z divided by the magnitude of z squared plus 1. x2 is equal to twice the imaginary part of z divided by the modulus of z squared plus 1. And x3 is equal to the modulus of z squared minus 1 divided, they got the same denominator, modulus of z squared plus 1. Right, so in terms of the xy notation, what you're looking at here is, I have a toy I like to have a toy that illustrates this better, but so let's see here. x1 is actually 2x over 1 plus x squared plus y squared, right? This is 2y divided by 1 plus x squared plus y squared, or if you like, x squared plus y squared plus 1. And this is x squared plus y squared minus 1 divided by x squared plus y squared plus 1. All right. So this is a one-to-one, well, not quite one-to-one, but it's a nearly one-to-one bijection between the complex plane and this unit sphere, which we call the Riemann sphere. How does this work? What's the point of this? It turns out that if you were to look at this map and how it goes from the complex plane to the sphere, you'd find out that it's a conformal map. So if you were to look at, like, two paths down here that intersected, and you were to look at their corresponding image up here, you'd find that the angle between the paths was preserved. It's actually a conformal map. However, it doesn't preserve distance. Like if you were to try to, say, take the distance between points between the plane and the distance between points on the sphere, you'd find that you have to modify your notion of distance in order to make those distances coincide. And that's an interesting story, but let me focus here. So you guys tell me, for these formulas, like, there's some things that are somewhat clear. For instance, when do you, what part of the complex plane maps onto the equator of the sphere? Let's just start there to try to understand the geometry of this for a minute. So what do we have for the equator of the sphere here?
Oh, the axes.
Right. Well, not axes. In other words, how do I get z equal to 0? I have, in order to get z equal to 0, I need what? I need this numerator is 0, right? So x squared plus y squared equals to 1 in the complex plane maps to here. So this is, if I have the modulus of z equals to 1, then that z maps to literally z comma 0, if you want to use that notation, like literally x comma y comma 0. That's what happens to the points on the unit circle in the complex plane. They just literally map to the equator of the Riemann sphere. Do you see how that goes down here? See how x goes to x? Because we get 2. If x squared plus y squared is equal to 1, this is 2. 2 over 2, 1. 2 over 2, 1. So we literally get x1 equals to x, x2 equal to y, x3 equal to 0, if the input is the unit circle. What happens, on the other hand, if we're outside the unit circle? Where does that go? Let's think through it. Outside unit circle, we have x squared plus y squared greater than 1, right? Which tells me x3 is what? Greater than 0, right? Inside unit circle, how's that go? That gives us x squared plus y squared less than 1. And if you look at the formula right here, that would mean that this is giving you x3 less than 0. So the way the stereographic projection in its current formulation works is it's mapping the outside of the sphere onto the upper half of the Riemann sphere. Right, the outside, like all of this out here, maps up here. And the inside of the unit circle maps to the lower half of the Riemann sphere. There's a way to just draw like a line. Here, if we look at it this way. So here's the North Pole. And I think if you just take the North Pole and you connect to a point on the plane, then like this point is Z, and this point is big Z. So inside maps to the lower part of the sphere, and outside the point on the Riemann sphere goes to the upper half. Where's the origin go? The origin in the complex plane maps where? The south pole of the Riemann sphere, right? Which is literally 0, 0, minus 1 in this formulation. So I said that the complex plane is nearly in one-to-one bijection with the Riemann sphere. Why is it nearly? What's the thing that doesn't get mapped to?
Nothing maps to the north.
Exactly, nothing maps to the North Pole. So this is what's done, is if I call this Riemann sphere sigma, all right, then I can say sigma we naturally identify with the complex numbers unioned with infinity. And infinity we think of as the North Pole. So if you want to work with extended complex numbers where you adjoin infinity, you simply do this. You map it in one-to-one correspondence with the Riemann sphere, and it works really nicely. So like, for example, if you were to look at an outer annulus in the complex plane, where does it map to under this? This mapping I'm talking about is the so-called stereographic projection. Stereographic projection. Again, it's conformal, but it doesn't preserve area. There's no faithful mapping of the sphere which preserves area. This is the map maker problem. This has been known for quite some time. So if I was to take an outer annulus, where it's coming from is like an open set around the North Pole. So a little open set around the North Pole corresponds to an outer annulus. So what that means as we go on in the course, if we want to think about a neighborhood of infinity, that corresponds to like an outer annulus. But it's literally like an open neighborhood of the North Pole on the corresponding Riemann sphere. And this stereographic projection, it also maps circles in the complex plane to circles on the Riemann sphere. And there's a lot more to say there than I can say today. But there's a lot to say there that, you know, you could give a whole course just on the Riemann sphere and all of the nooks and crannies and things here. Like there's so much to say. But anyway, so when we think about a Mobius transformation, we like to think about it not just on the complex plane, but on the extended complex plane. Because if we do that, then we can understand that it maps circles to circles. But we have to understand that a generalized circle includes lines. All right? And the funny thing is, you just saw in my example, is that a circle through the origin can give you a line which doesn't go through the origin. It's over here, apparently, right? But but on the other hand, what is the reciprocal map? How does it work? What is 1 over 0? It is no longer undefined. It is now infinity. The time has come. So don't tell the other engineers, like, no, tell them, come to this class. We make 1 over 0 a thing, you know? But it has to be understood in this sense, where there's just one infinity that we're adjoining to the complex plane. Anyway, so let me show you an example.